Slide 1, NETAN, TCP, UDP, and Circuit Emulation IP MPLS Transport Network. Good day, and thank you for taking the time to review the NETAN material in advance. Today, I will walk you through the slides you already have, but with the focus on how NETAN can be useful in a real operator environment rather than repeating the written content. NETAN is a network analysis and simulation framework that combines two traditionally separate worlds: static analytical performance modeling and dynamic time domain simulation. The key idea is to create a digital twin of an IP/MPLS transport network that is accurate enough to be used both for engineering decisions and for training automation, or AI-based control. Throughout this presentation, I will move from the overall concept into the network and traffic models, then into analytical results, and finally into dynamic simulation and AI/ML use cases. The example network you see here is intentionally realistic in scale, but fully synthetic. Slide 2, Agenda. Here is the roadmap for the discussion. I will start with what NETAN is and what problems it is designed to solve. Then I will explain how the network itself is modeled, including topology, equipment, and traffic. After that, we go into IP/MPLS design, routing, and link dimensioning. This is followed by end-to-end analytical performance results and what-if analysis. The second half of the presentation focuses on the time domain simulator, how it works, how it compares to analytical models, and why simulation becomes essential under overload and failure conditions. Finally, I will show how the same digital twin can be used as a training and validation environment for AI or ML-driven network control. Slide 3. What is NETAN? At its core, NETAN is a tool to model and analyze IP, IP/MPLS, and IP/carrier Ethernet transport networks at both access and core level. It supports multiple traffic classes that operators actually care about: circuit emulation for legacy or critical services, UDP for streaming and real-time services, and TCP for elastic or bulk traffic. NETAN can automatically create traffic routes from client sites to servers, or it can work with pre-configured paths such as MPLS LSPs. For each link and each end-to-end path, it calculates key transport metrics such as delay variation, loss, and unavailability. What makes it different is that the same model is used both analytically and in simulation. The MATLAB implementation simulates burst-level traffic, queuing, buffering, priority scheduling, and network events like failures or fading, all within the same framework. Slide 4. How can NETAN be used? NETAN can be used in two complementary ways: calculation and simulation. On the calculation side, it provides steady-state analytical results for transport performance, for example, delay and loss under normal traffic conditions, or under planned what-if scenarios, such as traffic growth or capacity changes. On the simulation side, NETAN models dynamic behavior. What actually happens when links fail, nodes go down, microwave capacity degrades due to rain, or traffic is suddenly rerouted. Because the same digital twin is used in both cases, NETAN is also well suited as a training environment for AI or ML-based network control systems, where you need a realistic but safe environment to learn from rare or extreme events. Slide 5. Network model, access, and core. This slide shows the overall structure of the example network. The access layer consists of 190 access sites that aggregate user traffic. Each site typically represents a few hundred users, but the exact number and traffic mix can be configured. The core layer consists of 64 interconnected core sites forming a resilient mesh. The core is responsible for transporting traffic between access sites and data centers or service platforms. The important point is that NETAN separates logical roles, access, core, servers, while still modeling the physical topology and link characteristics that actually determine performance. Slide 6, network model, configuration data. All network configuration data is stored in structured input files, such as network def Excel workbook. This includes site definitions, link properties, router characteristics, and client-to-server mappings. By separating data from code, NETAN allows the same simulation engine to be reused for different networks. In practice, this means you can start with a high-level model and gradually refine it as better data becomes available, without rewriting the core logic. Slide 7. Equipment models. NETAN includes abstracted equipment models for microwave, optical, and router platforms. The goal is not to simulate vendor-specific internals, but to capture the parameters that matter for transport performance, capacity, delay, buffering, priority handling, and availability. Microwave links, for example, can include capacity steps and fading profiles. Optical and packet platforms are modeled with realistic forwarding delays and capacity constraints. This abstraction level makes the model both realistic and computationally manageable. Slide 8. Traffic modeling. Traffic modeling is one of the foundations of NETAN because all performance results ultimately depend on how realistically traffic is represented at statistical level. We deliberately use simple but well-established stochastic models, what you might call classic M-type modeling, rather than overly complex traffic generators. The goal is transparency, analytical tractability, and alignment between analysis and simulation. Circuit-emulated traffic is modeled as constant bitrate. From a queuing perspective, this behaves as a deterministic arrival process, often denoted as D in Kendall's notation. This makes CE traffic predictable and well-suited for strict priority handling. UDP traffic is modeled using an activity-based source model. The number of active users at a site follows a binomial distribution, where each user independently toggles between active and inactive states. When active, each user generates traffic at a fixed rate. Statistically, this results in a superposition of many on/off sources, which in aggregate behaves close to a Poisson arrival process under typical conditions. In queuing terms, UDP traffic can therefore be approximated as M/D/1 or M/D/1/K, depending on whether finite buffers are considered. TCP traffic is treated differently. TCP is modeled as elastic, burst-based traffic, where both burst arrival times and burst sizes are stochastic. Arrival times are assumed to be memoryless, typically modeled as a Poisson process, M, while burst sizes follow exponential or heavy-tailed inspired distributions. This leads naturally to M/M/1 or M/G/1- type behavior at link level, depending on the selected service time distribution. The key point is that the NETAN keeps the same statistical assumptions in both the analytical calculations and the time domain simulator. Analytical models use closed-form or semi-closed-form queuing results, while the simulator resolves the same processes explicitly at burst level. By combining binomial user activity, Poisson-like arrivals, and realistic service disciplines, NETAN captures both average load behavior and short-term congestion effects, including queue buildup, delay tails, and packet loss under stress. Slide 9, IP/MPLS design. This slide shows how IP/MPLS service design is represented in NETAN, with a focus on service separation, priority handling, and predictability. Each traffic class, circuit emulation, UDP, and TCP, is mapped to its own MPLS label-switched path, or set of LSPs. These LSPs are not just logical tunnels, they carry explicit assumptions about priority level, bandwidth, treatment, and sharing rules. Circuit emulation traffic is typically modeled with strict priority and guaranteed bandwidth. From a transport perspective, this means CE traffic is assumed to see minimal queuing and is protected from congestion caused by lower priority services. UDP traffic is usually mapped to high or medium priority LSPs, with bandwidth guarantees or rate limits depending on design choice. This reflects common operator practice for real-time or near real-time services, where delay and jitter matter more than throughput. TCP traffic is modeled as best effort or low priority traffic. It is allowed to fill unused capacity, but is also the first to experience queuing and loss when the network is stressed. This behavior is critical to model correctly, since TCP reacts dynamically to congestion. NETAN supports both analytical evaluation of these MPLS designs, for example, calculating expected queuing delay per class, and time domain simulation, where priority scheduling, finite buffers, and dynamic interactions between traffic classes are explicitly resolved. This allows operators to evaluate not only whether a design works on paper, but how it behaves in practice under load, failures, or traffic shifts. Slide 10, IP/MPLS routing. For each access site, NETAN automatically searches for alternative routes to the assigned server. The shortest path is selected as the default route, and the second shortest as the backup route. Statistics such as hop count distributions are generated to validate routing design. This routing information is then used consistently in both analytical calculations and simulation. Slide 11, link level analytical performance. At link level, NETAN uses analytical models tailored to each traffic type. UDP traffic is modeled with deterministic per-user rates, while TCP traffic uses stochastic models with exponential burst size and inter-arrival distributions. From these models, NETAN derives queuing delay distributions and loss probabilities as a function of link load. Slide 12. Link capacity and dimensioning. Using the analytical results, NETAN produces link load maps and capacity utilization statistics. This allows identification of hotspots in the network and evaluation of alternative dimensioning strategies. The same framework can be used to test future traffic growth scenarios before any physical upgrades are made. Slide 13, static analytical end-to-end performance. Here we move from individual links to end-to-end paths. NETAN calculates path delay distributions for different traffic classes, showing best case, median, and worst case behavior. This is particularly important for services with strict latency requirements, where tail behavior matters as much as averages. Slide 14. Analytical what-if calculations. This slide shows what happens when traffic increases and backup paths are activated. Analytical models can quickly show how delay distributions shift under these conditions, providing fast insight into resilience and capacity margins. However, as load approaches or exceeds capacity, analytical models start to lose accuracy, which is where simulation becomes essential. Slide 15. Time Domain Network Simulator. The Time Domain Simulator models traffic at burst level with explicit queuing, buffering, and priority scheduling. It operates in discrete time steps and resolves how bursts traverse multiple links, accumulate delay, or are dropped under congestion. This allows realistic modeling of transient effects that analytical models cannot capture. Slide 16. Simulated versus analytical comparison. This comparison shows that under normal conditions, the simulator closely matches analytical results. As traffic increases, differences appear, especially for lower priority TCP traffic. Under overload, analytical models break down, while the simulator continues to produce realistic results by modeling finite buffers and packet drops. This validates both approaches and shows where each should be used. Slide 17, Event-Driven Simulation. NETAN supports explicit event modeling. Topology events include link and node failures. Capacity impairment events model microwave fading or modulation fallback. Service events can include server outages. By injecting these events into the simulation, NETAN can evaluate resilience, restoration times, and service impact in a controlled way. Slide 18, AI/ML training of network control. Finally, NETAN can act as a digital twin for AI or ML training. The simulator generates labeled data for normal and abnormal conditions, allowing training and validation of control algorithms without risking live networks. This closes the loop, from design to validation to automated operation, all based on the same consistent network model. Slide 19, Summary. Let me conclude with a short summary of what NETAN is and how operators typically choose to engage with it. At its core, NETAN provides a single, consistent digital twin of the transport network. The same underlying model is used for static analytical calculations and for dynamic time domain simulation. This ensures that design assumptions, performance results, and operational behavior are always aligned. NETAN models real operator traffic, circuit emulation, UDP, and TCP with realistic statistical behavior. It allows you to evaluate transport performance not only under average conditions, but also under stress, failures, and growth scenarios. As a result, decisions on design, dimensioning, and resilience can be made on a solid fact-based foundation. Beyond analysis, NETAN also enables future-looking use cases. By acting as a digital twin, it provides a safe and controllable environment for testing automation strategies and training AI or machine learning-based network control without any risk to the live network. Operators typically engage with NETAN in one of three ways. The first model is consulting and analysis. In this case, I use NETAN on behalf of the operator. The operator provides input data and scenarios, and the outcome is delivered as reports, figures, and concrete recommendations. This model offers fast insights with a very low entry barrier. The second model is assisted use and licensing. Here, the operator runs NETAN internally, supported by onboarding, training, and model adaptation. A one-time license of the NETAN codebase can be included. This suits operators who want to build internal competence while keeping time to value short. The third model is co-development and capability buildup. NETAN is used as a foundation for developing an internal tool or long-term digital twin. Models, features, and integrations are developed jointly with the goal that the operator becomes fully self-sufficient over time. This model is typically aligned with long-term automation or AI initiatives. Which model makes sense depends on where the operator is today and where it wants to be in the future. NETAN is designed to support all three paths,